All right, welcome back, everyone. I got a chance to review all your videos, and it's really nice to see all your faces. I hope you got a chance to review the other students in the class videos and get to be familiar with them somewhat. But this week we're going to dive into two lectures. We got pipes first, and then in the second recording we'll be doing valves. Split them up just because they are a little bit lengthy. And so hope these videos are helping you out. But like I said, please feel free to follow along in the PowerPoints separately, or just play this in the background and while you're doing laundry or something, whatever you're doing. All right, let's dive into it. So, when it comes to pipes, there's several parts to a pipe. The top of it's known as the crown, whilst the inside top, like the inside of the pipe on the top, is known as a soffit. At the middle of the pipe, you're going to have what's known as the spring line. Some of you have probably really heard that term before. As you backfill a pipe, you fill up to the spring line using haunching, and you compact that much first before compacting the rest of that dirt on top of the pipe. On the bottom inside, you're going to find the invert, and on the bottom exterior, you're going to find the belly. Within the trench, you got different areas. So below the pipe, you're going to have what's called the bedding. It says lower bedding, but anyway, yeah. On the bottom of the pipe, you're always going to have the bedding, what the pipe is laying on. And then you've got underneath near the pipe belly, you've got this haunch zone, and that's an important area to compact when you're backfilling. A lot of times that gets missed just because of the difficulties of getting to that area, but that's another important area of your trench zone. And then you got the upper bedding up to the spring line, and then from the spring line up, you're looking at side fill, and then you've got your initial backfill on top, followed by your main backfill. Now, the difference between the initial backfill and the main backfill is typically everywhere between, if you look off to the right, you'll see where it says embedment. So in that area of embedment, you're using typically like an SE30 sand. That's a sand equivalent 30, meaning it doesn't have rocks and that the material won't damage the pipe. Now, when you get above that, into that main backfill, a lot of times you're either using the native soil or you might be using like a class 2 base material, which is like a mixture of sand and rock to get that compaction. Also, when it comes to compaction, it varies from agency to city. I know a lot of cities require what's called a 90% compaction rate. However, for us at VID, we do a 95% compaction rate, meaning, it's just compacted more. And that's because it's a pressurized vessel. And the last thing you want is for that vessel to, come up out of the ground. So, having proper compaction around that pipe is going to prevent it from shifting and moving when you pressurize that line. All right, in the past, you had what's called cast iron pipe. You don't see this in the ground anymore. It's really corrosive. But for its time being, when it was put into, service, it did its part. It served a good purpose because, first before that they were using wood and, other structures that just, were not as sound. Uh, in this example here in the picture, you can see you got bell and spigot joints with the bell over here, or excuse me, the bell, and then you get the spigot that would fit inside there. But yeah, this is really old pipe. Like I said, it's super corrosive. You could get those graphite flakes, like it says here. And then, some cast iron pipe is still in service today, but typically it's being replaced with what's known as ductile iron pipe, which we'll get into. So you could see that, there's a molecular difference between the two, obviously. But the ductile iron pipe definitely has a little bit more flexibility to it. It's stronger. It's less corrosive. It's a all around better material than cast iron pipe. So ductile iron pipe, you've got several advantages. Like I said, good strength, durability, a little bit of flexibility to it. Um, long life expectancy. Um, but then you do have the cost of, the weight is always important. Anytime you're working with, any kind of materials, the weight of that is something you need to take into consideration just for a safety factor. Um, but then it can be corrosive in aggressive environments. So here you got some ductile iron fittings, so you've got T's, you've got reducers, 90s, you got spools, you can see there's a difference here between flanged ends and then push-on ends or plain ends. But there's a whole bunch of different type or types and styles of these ductile iron fittings. And then in here you can see kind of the breakdown of the ductile iron pipe. So you got different types of joints. You've got push-on or mechanical, which is probably a more common use of ductile iron pipe. It just, for speed and efficiency when you're installing mainline, having to bolt up everything is though, or, for like a mechanical end, takes time, or a restrained end takes time. But, like a push-on type will definitely go together faster and your production increases. Um, But like I said, you got different style. You got bell and spigot, flange, flexible ball, and these are the applications in which you would use them. And that's just like with any type of pipe. It all depends on where you're having to cross or what environment you're trying to get through will depend a lot of times on what type of joint you use. Like every pipe, there's going to be failures, and then you got to know how to repair these things. So in this example here, you could see, yes, we've got a hole, um, and sometimes you can weld, sometimes it's just a better idea to just go ahead and section in a fresh piece of pipe here. Here you can see, you've got these mechanical joints on each ends of this spool that are creating that seal after you cut out the section of pipe. Now this is probably two different scenarios here, but um, you get the idea. So the most common solution for repair is to remove the pipe entirely, or at least the damaged section, and replace it with the new pipe, which is it's going to give you a much longer uh, life cycle if you do it that way. So here's a nice little graphical representation of useful life, or pipe failure frequencies, with the different styles of pipe. You can see here, like we talked about before, cast iron pipe. It obviously failed here in the U.S., at a much higher rate than let's say PVC pipe down here. And again, a lot of this just has to do with the installation, the soil corrosiveness, could be system pressures. There's a lot of things that could lead to a break in a pipe, but you do happen to see the rate at which these types of pipe break. So if you're looking over here on the side, you can see that Canada is in the red, USA is in the blue, and you see that, different types of pipes, have failure rates either much greater or lower, depending on where they're being used. And again, that could do a lot with the soil, the installation type, the standards and specifications that are put in place. Steel pipe. Still used in today's systems. A lot of times you will see steel pipe above ground or below ground. When it's below ground, it's usually covered in concrete and has a mortar lining on the inside. But you have steel pipe when it's above ground. You don't necessarily need that outside cement coating on it to protect it from the ionic exchange or corrosion that can happen in the ground. But steel pipe has been used for a very long time. As you can see, early 1850s. So we're coming up on almost on 200 years of use here. But then you can go really small to, you can go 4 inch all the way up to, actually you can go smaller. You can even go 2 inches. I've seen 2 inch steel pipe. But for a water system, you're typically you see it, 4 inch to 144 inch, which would be 12 feet in diameter. And the manufacturing of it has changed over time. So like you can see, originally was used or put together with rivets. A lot of times now it's just a welded seam that you will have that can, closes that pipe up. Um, but yeah, this is just some basic information about steel pipe. Still really common in the industry today. Obviously, a lot of advantages to steel pipe in itself. Like I said, it's relatively lightweight until you start adding concrete mortar and lining to it, and then it becomes CMLC. But you can make a lot of special fittings. It can withstand high pressure, resistant to shock loads. Meaning, shock loads would be if you drop your pipe by accident, or I know that as when I was an inspector, I never allowed the contractors to just drop pipe from the top of the trench down into the trench because of those shock loads. I would always, if I saw them doing it, then I'd make them remove it and get rid of it. If they did anything like that, they should be lowering that pipe into the trench either by hand or by machine, depending on the weight. Some disadvantages, obviously very susceptible to internal and external corrosion. Water and metal or steel, they don't mix very well. But you're definitely concerned with external loads because even though it's steel pipe, um, if you were to get, a semi's driving over this every single day, that external load could definitely collapse that pipe. And then also it's susceptible to vacuum collapse. Uh, we'll talk about that in a little bit, or right now. That's right. So you got collapse, right? A vacuum collapse. And this is a condition in which there is no auto air vent that would allow air into the pipeline to prevent this from happening. And we'll talk about valves later on, but just a little heads up that, air vents are probably the most important valve in any distribution system. But here you can see, an image of a pipe that collapsed due to vacuum. So again, one of the disadvantages of steel pipes. All right, so you got black steel, you got welded steel, riveted steel. These rivets here is what we're talking about. And then you've obviously got galvanized steel. Galvanized steel, it was probably common back in the 50s, 60s. You don't see it anymore just because of the galvanic corrosion that takes place. I've gone to customer complaints, to their house where they said, "Hey, I've got no water," and then come to find out that their private side is, all galvanic pipe, and it's likely that they just sealed up. They corroded itself closed, in which they've got, a much bigger issue. Uh, and then over here, you can see this So going back to this riveted steel pipe, these rivets, you know, can negatively impact you, if they installed it where, let's say that the rivets are at, the 90-degree angle on it, because a lot of times, if this is a buried pipe, you would have services that need to come off at that angle, and at that station in which, that's happened to me before. So you've got to figure out a workaround, typically coming up a few degrees to get over it, but then you're having to bend that pipe and get that service to go. But you can also see here that they don't just run this rivets all along the same point on the pipe. Um, Reason being is that, it could lead to a catastrophic failure, but then it also, again, it gives you that option too. So, if you were to, have to install a service, let's say, where that rivet is, you could relocate that, potentially, and find an easier spot to install a valve or some kind of tap off of the steel pipe. Welded steel, very common. This is, used even today, all over America. Very common to see steel pipe in our system. And then same with black steel, is typically something you're going to find not in a distribution system as much, but maybe on a private system or a gas fitting. Again, different types of joints and then their applications. Um, there might be a couple questions throughout the semester, so just become a little familiar with them. Uh, but let's move on. CMLC, or cement mortar lined and coated, very common. you know. So what it's referring to is you've got this cement mortar lining that you see on the inside of this steel pipe, and then you've got concrete again on the outside, or cement on the outside, excuse me, that's coating the pipe. And this is all to minimize or prevent corrosion of this steel pipe while when it's buried. So when it comes to CMLC, it's a buried pipe. You'll see steel pipe typically above ground, or in a vault, but typically it's exposed, whereas CMLC is going to be a buried pipe. Lots of advantages, resistant to internal and external corrosion, so long as that mortar lining or the exterior coating isn't damaged. Um, can withstand extremely high pressure and loads on it. It's very long lasting. I've seen CMLC pipe that was put in, in the 50s, and I think actually no, that was AC pipe. Anyway, there was but I've seen some in the 50s that because the coatings on the pipe were so good, plus the cathodic protection, which we'll get into, was there. It looked brand new, even though it was decades old. But again, very heavy. Even a small diameter, short length piece of CMLC pipe can be extremely heavy. So, you definitely need to have heavy machinery anytime you're using it. And it costs a lot. But then, again, you got to figure out what's best, long term too, when you're looking at what type of pipe you're going to be putting in. Cathodic protection. So cathodic protection is the ion exchange between the ground and the pipe itself. So you'll have cations and anions that occur in the soil naturally, but it's an exchange of these ions. And if you have steel pipe or CMLC pipe in the ground, and there's an exchange of ions, it's going to lead to premature corrosion or failure of your pipe. So what the cathodic protection system does is it attaches a weaker metal to the steel pipe, and it's usually you've heard of magnesium anodes. Those are typically what's used on CMLC, is a magnesium anode. And that is what is going to degrade versus the steel itself. So you can see here, I took some pictures from a job that I had one time. Um, so you've got your welded ends here. They will patch this all up, but then they're going to expose areas on the pipe. And this is where they're going to attach what's called a structure wire. And this structure wire is then connected to the anode wires, and then and it's usually done through a shunt. I think I got a picture of it later on. But so these structure wires will be attached to the anode wires, and that's how you connect your anodes to your pipe, and that's so the anodes again will be what you know I guess get eaten away, if you will, over time. And then they get patched up. Everyone does it a little bit differently. It just depends on what agency you're at. But you might use some bitumastic cover over the pipe, and then also apply your CMLC. Everyone does a little different. This white wire here, this is just a tracer wire. It's kind of overkill. A lot of times when you're locating You should be able to detect steel pipe with your locating equipment, but here is, they throw on tracer wire for that pipe, so that way, it's easier to detect. Here's a nice little schematic of cathodic protection. You've got reference electrodes, you've got the CAD weld pipe for the structure wire, and you got your anodes here, and they're all being brought into some kind of a, well, in this case, it was a rectifier, but it could be brought into just a simple test stand. And it, so this is just a general um, diagram or schematic of how cathodic protection works. AC pipe. Yeah, definitely not used anymore, but it served its purpose back in the 60s, 70s, and even 80s. Um, before it was finally, recognized as a cancer-causing substance. And so, but at the time, it was lightweight, low cost. There was no metal, so that there was no corrosion factor, so to say. Very smooth, had a high C factor. But again, AC pipe, it was very easily to damage. There's just, it had its issues, but nowadays it's a hazmat. So when you come across it, typically you have to treat it as such. And so AC pipe removal is, conducted. A lot of times, the smaller diameter AC pipe is what tends to fail more frequently. But the larger stuff was thicker. So it actually still looks pretty good. I came across some 1940s AC pipe. I think it was like put in 1948, and I mean it looked brand new. It was, but it was like I want to say it was 12 inch, and it looked brand new. I mean, still worked really well. I mean, so long as it's wet, it's not going, it's not friable, and so therefore, there's no hazard, at least with breathing it in. The material itself is still hazardous. So here you can see, the friability of that pipe, like I was talking about. This is what I'm referring to. If this stuff, gets into the atmosphere and is blown around, it can, you can't breathe it in, and then what happens is, it leads to what's called mesothelioma, and basically your body tries to, attack the the asbestos fibers, and it basically acts like a cancer almost, and basically kills you from the inside out. It's a long, slow process. It can take sometimes, 20 plus years for itself to to materialize and then create this problem for you. Anyway, um, it was widely used in water distribution systems. It was widely used in every industry. Asbestos was a great material until we realized how bad it was. It's used in all kind of brake pads, filters, all sorts of stuff. But yeah, as you can see here, it was finally banned in 1989. And that's because, right, PVC pipe, the most common used pipe in the industry today. High C factor, meaning this interior smoothness is really good. Water flows nice and easily through it. Low cost, it's lightweight, easy to install, easy to handle. However, because when you have lightweight and easy to install, it's usually tied to the disadvantage of susceptible to damage, and then tapping issues. In the past, the manufacturing of PVC pipe has improved over time. In the past, the fibers that are used to make PVC pipe used to be all very uniform and not like a cross stitch pattern. So if you were to install multiple surfaces at the same bearing on your pipe, it could lead to a stress fracture or and create this crack that would travel the length of the pipe. So that's why when you're installing water services on PVC pipe, you want to offset them by, 7 to 15 degrees in order to prevent this linear weak point on the pipe. But definitely susceptible to UV damage, permeation. So, if you've got leaking, let's say, fuel tank at a gas station nearby, you run the potential of that being able to penetrate your pipe. Obviously, it's not conductive, so you have to install some kind of tracer wire in order to be able to find it after it's been buried. They got a couple different types of PVC pipe joints. Again, bell and spigot. Here's a nice little cutout of it. You can see you've got this rubber gasket that's in here, and that is what's creating that seal. Um, and then over here, you've got restrainer joints. You can see how, I don't know why it's changing color. I don't know if it's happening. But yeah, you've got restrainer joints, different types. And what's happening is you've got this ductile iron fitting. You've pushed your pipe into it, and then these restrainers here have like little grooves in them, and so you bolt that together, and it's going to hold that in place. On this valve down here, you can see that it has restrainers built into it, and then also connected there. It looks like you've got a T. It looks like they all have some type of a restrainer on it, and that's used to just help hold that valve in place. Um, this setup that you see down here on the bottom is not something that I would personally install. Typically, I'd use like a flange T and then bolt the valves to the T, and then I guess support them that way. But again, this is a picture that I found and thought it was interesting with how they were using the restrained joints for this setup. So like I said earlier, you want to, at the beginning of this presentation is that you want to make sure you have proper compaction around your pipe. If you don't get that proper compaction around your pipe, it can lead to the pipe collapsing, as you can see in this image here. But by having proper compaction around your pipe, you're going to prevent this kind of a scenario from happening. Down here, you can see here's that that crack that travels along the length of the pipe here as a weak point. And, this is probably an old PVC pipe. Like I said, nowadays they do like a cross stitch or cross fiber manufacturing technique that has minimized or prevented this from happening more commonly. In the lower right image, you can is what you call or it's a black line on the pipe. This one actually has two of them, and that's called a home line. And so when you install the spigot into the bell end, you only want to go as far as you see that, where you only see, in this case, one of these lines. And that lets you know that you've installed the spigot end into the bell end far enough and if you overstab it, you could lead to the what you see happening on the image in the upper right corner. And what happens by overstabbing is you take away that slight flexibility that's built into it. Also, if this kind of damage happens, the manufacturer can just as easily say, "Hey, you did not install this pipe per our specifications, so you're at fault for this break." But if you have pipes that are installed correctly and per the manufacturer's recommendations, you can a lot of times, uh, you know, have them uh, pay for whatever kind of damage that maybe prematurely happened to the pipe. Again, here's that same image. You can see that, when you compare PVC pipe to every other style of pipe that, we use in the water industry, PVC pipe has the lowest water main break rate out of all the materials. Copper tubing, really common in the water industry, especially for water services, or maybe small, really like 2-inch mains sometimes will be constructed of copper tubing. Copper tubing has a lot of advantages, and let's get into that. So, um, interesting. I saw a video the other day of how they used to use lead in the past to make our water service. I'll see if I can't find that and maybe upload that for you guys. but it was quite interesting. But obviously, we understand the issues with using lead pipes or lead fixtures in, or the effect that it has on the neurological system. So copper then, of course, took its place, and is widely used throughout the world in plumbing. It's a strong material, but it's also flexible and easy to work with, lightweight, good material all around. There's different types of copper tubing, type K being the thickest. And one way that I tricked my, or taught myself into remembering, which type of material to use in its applications is with type K copper. You could walk around and say, okay, where is this pipe? And it's typically buried. So that's how I would know that type K copper should be what's being used in the ground. You have type L copper, and again, something mnemonic that I use is, that type L, so I can look and see the type of, the copper itself. So type L, and then you have type M, which is another type that's used in like residential buildings and whatnot. Uh, Many different joints, ways of connecting your pipe. You could do a flared in, you could do a mechanical compression, solder joint. There's all kinds of different ways to connect pipe or copper tubing. But really important here, I want you to see this, is that copper tubing kills pathogenic microbes. So when if you have a copper service lateral and you pull a back T sample off of it, I'd say 9 out of 10 times it's probably going to pass due to the fact that the copper, it will kill microbes. Um, so you might see something on that again in the future. Really long lifestyle, and of course, resistant to high pressures. So selecting pipe materials is obviously a big issue. One of the concerns anytime you have any kind of a mainline project, typically you're going to look for the most uh, cost efficient way to install any material. However, you also again have to look at your environment and see, what are you dealing it with, and how are you going to, get the pipe or get the water, from its source to its end user, and that pipe and getting the right one is the right, how you figure this out. There's different sizes. There's, um, a lot of factors that you have to take into consideration. And so really just going through this questionnaire right here can help you figure out what type of pipe materials you're, going to need. Again, consider the pipe characteristics, its strength, its pressure rating, durability, corrosion, um, ANSI, NSF standard 61. Um, any type of material that's used. It's actually the ANSI NSF 60 and 61 that you have to pay attention to. Anytime you're using anything in a potable water system, it has to be NSF 61 compliant. Whether it's a chemical, it's the pipe materials, it has to meet that standard. And that is the National Sanitation Foundation. That's what NSF stands for. And then the uh, excuse me, the American National Standards Institute. Cost is obviously going to be the biggest driving factor of any pipeline installation. Excavation will typically be the most expensive uh, factor in any pipeline installation, not so much the materials, but the actual excavation itself. So, you can see here you got some cool images. You got reducers, you've got 90s and T's and angle points. You can see the challenges that go into installing any pipe in itself. But more importantly, safety is probably going to be your biggest factor. So looking at what they have here, um, obviously I don't see any ladders anywhere, and these guys are clearly working in trenches that exceed 4 feet in height. So safety, biggest factor here. But and that could be associated with the cost. If you, the developer, the contractor company, like you can all be taken to court if something should happen. So just because it's not you in the trench or your company in the trench, if you're associated with it, people are going to come after you. So again, you got to consider the types of soils that are involved. You know, are you crossing a river or a highway? Are you near a railway or going underneath a railway? There's a lot that goes into, being able to get your pipe from point A to point B. Again, installation, the trenching operation is going to be your most expensive, factor in any installation. Um, Trenches are usually, well, it says 1 to 2 feet wider than the outside of pipe. Reason being is that you don't want to have to dig out more than you really have to. And then, because you're going to have to backfill everything. You're going to, you don't want to create more work for yourself than you really need to. So even though the working conditions might be tight, there's a good reason. Depth is obviously a factor in areas where it freezes. Frost can be a factor. So typically, you're going to bury your pipes deeper in areas where it freezes to avoid that frost zone. You have, of course, safety factor, like I talked about. Soil conditions is also, important to consider. All right. So when you're laying pipe, you obviously want to make sure you have the proper shoring to protect yourself and everyone else. You want to inspect your bedding materials. Again, that's just checking, make sure that you're using the proper SE30 sand equivalent, so that way you don't have a whole bunch of rocks or anything that could eventually like wear a hole or, bore a hole through a pipe through the vibrations as water passes through. Obviously, cleanliness is a big thing. So you making sure that you don't have anything inside the pipe that could create water quality issues. Let's see, some of the other big things on here. Pressure testing your pipe is a big one. That's one way we can check for leaks prior to placing a pipe in service is doing a pressure test. And again, that's something that's different at every other agency. There's no one standard that states this is how you're supposed to do it. Uh, Flushing and disinfection. Again, everyone, these are things that everyone has their own way of doing it. When I did it, I would have them chlorinate the pipe to 100 parts per million and then let it sit for 24 hours. And then it couldn't lose more than 20% in that 24-hour period. If it passed that, then they could flush, and then we would collect a back T sample. Back T samples are um, going to give you an indication if there is any issues with the water quality in that pipe. It'll let you, know if there's bacteria in the pipe. We hear, a- again, I got air vents listed on here. Again, that's, you know, going to be one of the most important valves in the system. As-built drawings, again, very important. That lets us know exactly how the system was constructed. So safety, again, big issue. I mean, honestly, you could teach a whole semester on safety. There's just so much that goes into it in this industry specifically. So if you look in that upper right hand corner, you could see the different types of slopes that you can work with, and that all depends on the type of soil. If you've got, rock that you're digging through, then, or, it's considered type A soil, and, you can use 90 degrees, but as that soil type varies, especially around here, if you're along the coast, you've got beach sand. I mean, you're really not doing a sloping for your safety. It's so much digging, so much excavation, yet it takes up such a large footprint. It's just not practical, which is why you have shoring and shield boxes and sheeting that are typically more common. Um, the sheeting, the way it's different from shoring is that it's still using some kind of a shoring jack. It's that you're installing a sheet in addition to it to prevent, the sides from failing or falling in. If you've got like a type B soil, doing shoring is definitely a practical approach because you're not worried about the sides sloughing off or falling in. But then shoring box is probably going to be your safest bet. The important thing and difference between the shoring box and the shoring or sheeting is that this shielding box has to stick up above the top of that trench. That's pretty important. Getting into the bedding, um, you can see here there's the right way to do it and the wrong way to do it. You've got the bell and spigot ends, so you want to dig out a little bit at those points. One, when you connect the pipe together, you don't want to be getting dirt inside your pipe, so having that dug out below it will help to prevent that from happening. And then you want to have an even support of that pipe all the way across. Obviously, you don't want to have just, poor bedding without it being level, or else you're going to have, support in one area and not another area, and that can lead to pipe break. Here's again, we're getting into the spring lines and the different types of beddings and the importance of these. Feel free to go through these. It kind of gives you a little bit more of a descriptive breakdown on bedding. Inspection and cleanliness, right? Obviously, if you have a clean work site and you have clean pipe installation, you're going to save yourself a lot of time in the long run. Um, it, it's important that cleanliness, even though you're working in dirt, is achieved. It's going to minimize the chance of something getting into the pipe or something crawling into the pipe. So you definitely want to make sure that at all times you're keeping in mind and cleanliness and then inspecting for it yourself. Even though you may or may not be the inspector, as the worker, you yourself should be checking for these things. Right here you can see we're talking about placement of pipe now, and this goes for any type of pipe that is. You want to make sure that you are placing the pipe in the trench and not rolling it or dropping it into the trench. And placing it, like I said before, by hand or some kind of mechanical means. Typically, you're going to have the bell end is normally laid in the direction of the work, um, and then you would stab that spigot end into the bell end. Uh, Except for on slopes, then it is reversed. When you're working on a slope, you would reverse it. It's just for ease of installation. Pipe joints, again, it's going to depend on the application and the environment, which type of pipe joint you're going to use. In most cases, you're probably going to use that bell and spigot end because, like I said, for production purposes, it's much faster. But there will be times where you will need to do a flange joint or a restrain joint. Again, this is a bell and spigot, but you've got these restrainers on here to help hold that together. Um, an area where you might want to use this is if you can't install a thrust block, which is a concrete block that's poured around the pipe or behind the pipe to prevent it from shifting and moving. If there's other utilities in the way and you can't meet the requirements for the size of that thrust blocking, then a restrainer joint can help in that area. And then down here you've got like a welded butt strap that's going over the two plain ends, and that will be for steel pipe. Here we have a ball and socket. It's made to be restrained and can provide deflection up to 15 degrees. Again, you're likely if you're crossing some kind of a water intake or river crossing, this is the type of joint you want because you want that flexibility. You want that pipe to be able to move, or have that flexibility from the forces of those streams. Um, it has both bolted ends or a ball and socket type. But I've never installed one of these. I've never had to use one of these. We never had to cross any streams in the time that I was in construction or inspection. All right, tunneling. This is something I've gotten to see a few times, and it's pretty fascinating. It's a very slow process, but if you ever get the opportunity to watch tunneling happening, it's pretty cool. It's just a different method of installing pipe. Well, really, you're not installing. First, you're installing a casing first, and then you attach. Um, these fittings to center the pipe as it goes through the casing. It's a lot of work. It's super expensive, but it's typically to get yourself underneath some other kind of structure, like a storm drain structure. The last thing you want is to have a main break on your pipe below one of these big structures and not have that casing where you can just pull that pipe out and make your repairs and then send it back through. Um, but yeah, tunneling is another means and methods to getting your water piped from point A to point B. So like I talked about previously, thrust blocking is a mathematical calculation. It has a lot of things that are taken into consideration, such as soil type, safety factor, depth, um, pressure. So all of these factors get considered when, calculating out the size of thrust block that needs to be installed. So on the bottom left here, this is just a thrust block chart that VID has put together, which specifies the size of the thrust block depending on the size of the pipe and the soil type and pressure. And then there's, if you look onto the right, you could see, all the different angles and ways that thrust blocks can be installed. Same with the center. All right, air vents. Like I said, this is, in my opinion, the most important valve in any system. So let me make the argument for it. As you can see in this center top right or top image, you've got a pipe here where there's only corrosion on the bottom half of that pipe. Reason being is because there was airlock inside of this pipe, and so this pipe never was used, like the full diameter of that pipe was never utilized because of this airlock. Now, you could say, well, only half of that pipe is corroded. Well, that's, something that's going to get changed out over time anyway. But water and air do create water quality issues. So air vents can prevent, poor water quality. And then, like I showed you that image earlier of the steel pipe that had collapsed, and that was due to a vacuum inside that pipe. So air vents would, an auto air vent, or combination air vent would have prevented something like that from happening. There's two different type or styles. You've got an automatic and a manual one. Manual air vents, at least in our Vista's distribution system, are pretty common. We tend to put combination air vents at the end of like a dead end or somewhere where you're typically not moving water, and so it's creating that vacuum condition. Backfilling, definitely one of the important aspects to any construction of a pipeline. It supports the pipe. It will carry surface loads. It provides that lateral stability. Again, haunching is something that you want to become familiar with. You'll probably see it again on a quiz or something, but it's that backfilling under that pipe, like we saw in that one of the first slides. Jetting is another method of backfilling. Personally, we don't want to use jetting in our system. You can achieve really high density and compaction with it. But again, when you have to go back and dig up a pipe later on, it creates more work just because that backfill is so compacted and so hard. Um, in the bottom center there, you can see that's called a sheep's foot, and that's used with heavy machinery and used to compact your trenches. And then you've got the whacker on the right there, and that's probably more common than anything, especially inside the trench or near the pipe. You're going to use a whacker just because you're less likely to damage your pipe. So after your pipe has been backfilled and passes compaction testing, you're going to want to conduct a pressure test on that pipe to ensure that all of the joints are sealed properly and you have a nice tight installation. So what is a pressure test? It's the water main's ability to hold pressure and to determine if there's any leaks. Uh, Leaks. So when if it can be deceiving sometimes as you're doing a pressure test. If you notice that the pressure drops slightly, it could be that there's still air in the line. So you always want to afford the contractor or the company the opportunity to flush and get all of that air out because air is compressible, whereas water is not. So you typically want to pressure test to 1.5 times the operating pressure, or it says or 150 psi. But just to give you an example of a 1.5 times, if you have 100 pounds of normal static pressure in your pipe, you're going to want to test it to 150 psi. The length of the pressure test varies between agencies. I know for VID we use a 1 hour test, and it's zero loss. You can have no pressure drop whatsoever. Um, AWWA standards allow for small amounts of leakage based on that pipe and joint, but at VID I always ensured that there was zero loss at every pressure test that I conducted. So what could lead to a failed test? Well, there's a lot of different things here, and you can go through the list off to the left here, such as foreign, material, testing too much pipe. The limit that we established was 2,500 feet. Um, what happens when you have a lot of pipe is that it's hard to detect if there really is a leak in small sections of pipe, small diameter pipe, and small lengths of pipe. If there's a pressure leak or there's a leak of some kind, you're going to see that pressure drop right away. But when you have a large diameter pipe that is long in length, detecting those leaks becomes much more difficult. It's just it doesn't show up on the gauge as well. What can cause it? Like I said, forgetting to tighten bolts, your faulty pump or gauge could cause it. Um, Entrained air, that, like I said before, air is compressible, whereas water is not. So if you apply pressure and there's air in there, the gauge will drop. Not enough saturation time. That's for CMLC pipe. So concrete or mortar is permeable. And so if you install CMLC pipe, you need to let it soak for 24 to 48 hours before doing any kind of pressure test to allow that water to, saturate that mortar lining. Otherwise, you're just going to fail your test. After you pass your pressure test, you typically want to flush again. You want to try and make sure that that pipeline is clean. You want to flush at a velocity of 2.5 feet per second. Reason is that it's enough velocity to scour that pipe and remove any kind of debris without creating other issues. As you scour, anytime you're flushing a line, if you have an existing system that is flowing into that, what can happen is that biofilm that develops on the inside of a pipe can start to scour off and create water quality complaints from other areas of your system. um, I've seen that happen a few times. So You don't want to flow at too high of a rate, or you can be creating more work for yourself. But you want to make sure that you do it long enough to have at least two or three complete volume changes of water in the pipe that you're flushing. Next step would be to disinfect your pipe. Couple different ways to go about it. Um, Most of the time, you're going to have some kind of a continuous feed method. You're just slowly injecting chlorine. On here, it's saying 25 milligrams per liter for 24 hours. However, I would always do 100 parts for 24 hours. You don't, the reason you don't, like you don't want to do too much, but you want to do enough that you ensure that, you're disinfecting your pipe. Here you got the slug method, which is 300 milligrams per liter for 3 hours. Um, if you use super high concentration of chlorine, one of the things that can lead to is degradation of the rubbers that are used to seal your pipe. And so that's why you typically don't want to leave that high concentration of chlorine in your pipe for very long. Um, In addition to that, there's the tablet method, not real common. Some people, some contractors try to go that way, but I would always enforce, the continuous feed method, just because it has a much higher success rate. So, like anything, we always talk about it, is there a way to calculate out how much chlorine is going to be needed to get to that 100 milligrams per liter for your 24 hours? How many pounds of chlorine are needed here? So, in our case, in this problem here, you've just finished installing 2,300 feet of 18-inch water main and need to dose it to 100 parts. How are we going to do that? Right? Well, let's get into math because there's always math. All right, so you want to convert the pipe volume into million gallons. So taking that 2,300 uh, feet of pipe uh, and then your 18-inch diameters and running those numbers real quick. You should all be pretty familiar with that. So if you did the math on that, you're going to come up with a 0.0303 million gallons. Next step, solve the equation using the pounds formula. This is something that we'll dive into in, I believe it's next week's lecture. There, I've got a different way of doing these pounds formula, and it's proved to, well, it's helped some people with understanding how to, do these calculations. So we'll get into that, but I believe in this case here, we're just going to go straight across and just plug and play, right? So 100 parts per million times 8.34 pounds per gallon. That 8.34 is a constant. And then times million gallons, which will give you 25.3 pounds, and that's pounds of chlorine needed to achieve 100 parts per million in that pipe. Dosing calculations. Like I said, there's tons of math. There's always math, right? So here's another example. You got 1,700 feet of 24-inch DR14. DR14 is a classification of pipe. So you've got different types of pipe, right? So PVC pipe, SDR35 pipe, and they have a DR rating to them, and it's really just like the thickness of that pipe material. All right, so the company hired to chlorinate the main is instructed to chlorinate to 100 parts. Upon arrival, they say you have 25 pounds of chlorine with them. Is this enough? Let's find out. So you do the math, you figure out what the volume is in million gallons. Then you plug that into your pounds formula, and you realize, nope, it is not enough. Bacteriological testing, extremely important for any water distribution system that is newly constructed or one that has been repaired and you're putting it back online. Um, you're going to want to get two samples or go through two rounds of this. So basically, the way you've got this bacteriological bottle or vessel, and inside of that is called sodium thiosulfate. And what that does is that it neutralizes the chlorine from the water. And the reason you want to do that is because you're trying to determine is there bacteria in the water. Chlorine obviously is a disinfectant and will, eventually or potentially eliminate that or sterilize or not sterilize, disinfect your water. But you want to know, is there bacteria in there? So you collect the your water sample, up to 100 milliliters inside this bottle, and you mix it with that sodium thiosulfate, which is going to eliminate the chlorine. Then when you take, these samples are taken back to a lab, they put in what's called like a colert, which is a bacteria forming agent, and that mixes, with the water, and you let that incubate for 24 hours. Or there's other kinds that are, 18 hours, but 24 hours is the most common. And so you let that mix for 24 hours. And at the end of that, if that sample has turned into like an orange or a yellow, that's positive for total coliforms. Now, bacteria, there's so many different types of bacteria. We're not going to get into that, but it's an indicator to say yes or no. Is there chlorine or bacteria in the water? So if it does turn yellow or an orange, then that's an indication that yes, there is some kind of bacteria in the water. Now, if you shine that under a UV light and it fluoresces, then you know it's positive for E. coli. So, anyway, that's just kind of how a bacteriological test works. But you want to do two rounds of it. You want to collect one sample and then you collect the second one, which is just a confirmation to make sure that the results that you received from the first one are in fact true results. And so you want to make sure that, before you put any water main in service, that it is good to go and you're not going to have any kind of water quality complaints. All right. After it's passed all its testing, you can connect it to the existing system. Um, here's an image that I took one night while working over in Vista off of Huff Street, where you you've just got multiple couplings. Anyway, it was just I figure it was kind of an interesting night. Anyway, you always you always come across stuff in the middle of the night and that you could tell was just put together with the thought of looks good for my house. Um, so. Uh, Anytime you're connecting, it's often going to require a shutdown of some sort, so that way you can tie in. Connecting to systems that are decades old can be tricky because sometimes the records aren't that great of what was actually put in the ground, so you might come across a lot of stuff that you didn't know would be there. Here in this image here, this one joint right here is PVC. And you can see you've got AC pipe with an AC coupling on PVC with another AC coupling, and then this short little pup of AC pipe connected to more couplings, another coupling. So, like I said, preparation is key. You always want to excavate out your connection point so you know you're exactly what you're getting into before you have to actually tie into it. Last thing you want is to open this up in the middle of the night and realize, what a CF it is, and not have the proper materials that are needed to connect to that pipe. And then site restoration. After you're all done connecting and everything, you put it back into service. You want to also, re-beautify it, if you will. You always want to make it look like you were never there. That's just being a neighborly thing to do. These images that you see on this slide are actually of Dubai. When I visited Dubai, it looked a lot like the image on the left. And then as time went on, obviously it is what it is today. And you can see that here. Uh, Equally important, as-built plans, you definitely want to have very detailed, accurate information of how that pipe was installed. A lot of times you have easement rights or you get easements during the design phase. And if that pipe is installed outside of those easements, well, you're going to have a lot of trouble accessing them and being able to make repairs to those kind of things because people, they love their easements. So, showing a very detailed description, both in a profile and plan method or design or schematic, excuse me, um, are helpful. So that, depth is never guaranteed. Obviously, the depth will might change just due to paving operations or what have you. But the layout, the plan view should definitely stay the same. Like, that should be, very accurate anytime you go to have to dig up a pipe later on. All right, one more problem before we hit the road here. How many pounds of chlorine are needed to disinfect a water main holding 53,000 gallons of water to a concentration of 25 gallons or 25 parts per million? So I've got the triangle. Sometimes I use a pie, so it's in a more circular form here, but let's run through it real quick. Parts per million times 8.34 times million gallons equals pounds per day, or pounds, excuse me. So first we got to convert that 53,000 gallons into million gallons. Gallons crosses out. You're left with 0.053 million gallons. So then when you times that by 8.34 times the 25 parts per million that you were trying to achieve, you're going to get 11 pounds of chlorine needed. All right. If you got any questions, feel free to send them my way. Have a good day.